The Laplace transformation is an example of what is called an integral transformation. As we have seen earlier, it is based upon an integral, and the integral is known as the Laplace integral. I am not going to go into any great details about the theory of the Laplace transformation. One has to do it really properly, although for the purpose of our application we may not have to go too far into it. Still, as electrical engineers, we should know sufficient about it. So, as I said earlier, it looks like an integral. The only trouble is that it is not the commonly used definite integral whose limits are numbers like a, b, or 0, 3, and so on. Here the lower limit is 0 and the upper limit is infinity, and I have put this infinity in inverted comma to indicate that it is not being regarded as a number, but actually what is involved is a limit. So, strictly speaking, we should be talking about the limit. So, therefore, lim of, let us say, integral from 0 to an upper limit of the integral, that is capital T, and the limit as t increases without any bound, or the limit as capital T tends to infinity of the integral 0 to t of the function, and for us the input function is denoted by ut. So, if I am looking at the Laplace transformation applied to the input function ut, and this is multiplied by exponential of minus st dt integrated over the interval from 0 to t, and the limit of this integral taken as t increases without bound, or as we say, as t tends to infinity. I pointed out that we have in the exponent the number s, which can be a complex number rather than just a real number, and because of that, even though the function ut, which is a signal, physical signal, corresponds to a physical signal like maybe the applied voltage as a function of time, or it can be an output variable like the speed as a function of time, and so on. Ut is a real number, or u is what is called a real valued function. The result of this integration will in general be a complex number, and I had asked you to work out a problem, a simple problem that involves the calculation of this integral for the function u given by the sine function, that is ut given by sine of t, and for a particular value of s. Now, this is where one has to be aware of something, although as I said we will not go into any great depth. This integral, or rather the limit of this integral, may exist, as we say, or may make sense or be meaningful only for some complex numbers s, and not necessarily for each and every complex number s that you may think of. For example, if we go back to the function sine t, then if I look at the integral 0 to t sine t in place of ut multiplied by e to the minus st and integrated over this interval, and the limit of this as t tends to infinity, then this, I told you, will turn out to be 1 over s squared plus 1. In fact, I asked you to work it out for a value of s which was different, for a particular value of s rather than for a general s. It turns out that this makes sense, that is, the limit is equal to this number 1 over s squared plus 1 only for certain complex numbers s. For example, here the complex numbers for which this integral will indeed, as one says, converge or have a limit. It's not enough to just write limit, there should be a limit should exist, or a limit should be possible. Now, that will happen for the function sine t only for certain values of s, and these values of s are given by, as one writes, real part of s greater than 0. If you choose a complex number which does not satisfy this condition, real part of s greater than 0, that means the real part of s is positive. For example, what would be an example of a complex number whose real part is positive? Well, 1 plus j1 is a complex number whose real part is 1, which is positive. The number 0.5 plus j0, or you can think of it as just a real number rather than a complex number, although as a real number it is also a complex number, then 0.5 plus j0, its real part is 0.5, that is also positive. So for such numbers, for complex numbers s whose real part denoted by real s, real part of s is positive, this integral will converge and the limit will indeed be equal to 1 divided by s squared plus 1, not for other s. So once again, as an additional exercise, you can put, as a very simple and special case, put s equal to 0 and find out what the limit is, or whether the limit exists at all, that is whether the integral converges. Then you can try, for example, s equal to j or j1, a purely imaginary number, and find out once again whether the integral converges, that means the limit exists or makes sense. And of course you can try it for 1 plus j1 and check that the limit does converge, and the formula 1 over s squared plus 1 gives it correctly. So this set of real numbers s for which the Laplace integral converges or the limit exists is called the region of convergence of the Laplace transform of the function, or the region of convergence for the particular function that we are talking about. So the function sin t, the region of convergence for its Laplace transformation is real part of s greater than 0, and I had already made use of what is known as the complex plane. So if one uses the complex plane, here is the real axis of the complex plane, here is the imaginary axis of the complex plane, then one can find out what are all the s complex numbers s for which the integral converges. For example, for sin t, here is a complex number 1 plus j1 for which the integral converges. Here is the complex number 0.5 plus j0 for which the integral converges, and there are many more, and that is the region of convergence. And then one can show it in the complex plane as a region by the usual engineering method of hatching the region. So for example, I have done this. The only thing to remember about this hatching is that the imaginary axis is not a part of the region of convergence for sin t. The region of convergence therefore is all the complex numbers whose representative points or representative points lie to the right of the imaginary axis. Now this part of the complex plane is referred to as the right half plane. We will abbreviate it as RHP, right half plane. Now this region of the complex plane will play a role later on when we talk about stability of the feedback control system. So remember this region of the complex plane which is to the right of the imaginary axis, in other words the set of complex numbers whose real part is positive, is called the right half plane. And naturally the region that lies on the other side of the imaginary axis, the region to its left, so I will show it by a different hatching, this is the region to its left, that will be called the left half plane, LHP for short. And so one can think of the complex plane as being split into three parts. There is the imaginary axis, there is the right half plane to the right of the imaginary axis, right of course when we draw the diagram in the traditional way, or the region where the real part of the complex number is positive. Imaginary axis is the set of points where the real part is 0, the number is purely imaginary. And then the third one is the left half plane, the region where the real part is negative. So this is the breakup of the complex plane into three parts, which plays an important role in the study of stability of a feedback control system. The left half plane, the right half plane, and the imaginary axis. Sometimes instead of left half plane one says strictly left half plane, sort of emphasizing that the imaginary axis is to be excluded. Similarly, we can talk about the strict right half plane, which means numbers or points which lie strictly to the right of the imaginary axis, not on it, that is not to be included. only those which are to the strictly to the right, but usually LHP and RHP will mean strictly to the left and strictly to the right, so one need not always say it. So the function sin t has a Laplace transform, that is, after applying the integral transform to it, we get a function which is given by 1 divided by s squared plus 1, but this holds only for certain set of numbers s. So in other words, the Laplace transform of sin t, the sinusoidal function t sin t, is the function 1 over s squared plus 1, but only for the set s given by real part of s greater than 0. So I am writing it here this way, the Laplace transform of sin t, and one starts using abbreviations. So I will say L, this letter is called script L, that is very commonly used in most textbooks. Script L of sin t is the Laplace transform of the function sin t. It is a function which is defined for some complex numbers. Which ones? Those for which the real part of s is greater than 0, and at a complex number s satisfying this condition, the value of the Laplace integral is 1 over s squared plus 1, and therefore the value of the Laplace transform is 1 over s squared plus 1. So you can now understand why it is called a transform or the Laplace transform, because you start with a function which is for us something called a signal or a variable, time variable, some signal, some variable that changes with time. For us it is the input or output or some other variable, speed, pressure, voltage and so on. Whereas after doing this business of computing the integral and so on, what results is a function which is defined on complex numbers and whose value is also usually going to be a complex number, and this is called the Laplace transform of the original function or of the time function sin t. T, of course, whenever we are using t as the significance of time, this s right now will have no significance, although in communication theory one can relate the Laplace transform to another integral transform, and what is it? It is the Fourier transform, named after Fourier. It is also an integral transform. It also involves this business of infinity somewhere, so that also has to be handled carefully. There is a relationship between the two transforms, the Fourier transform and the Laplace transform. These are two major integral transforms which electrical engineers have to know. There are a few other integral transforms which also find applications in electrical engineering. One such is called the Hilbert transform, named after Hilbert. Here the Laplace transform is a complex valued function of a complex variable and defined only for a particular region of the complex plane called the region of convergence. And here again there is more or less a commonly used notation. If the function is denoted by a symbol small u, the function of time so to speak, this is called the original function, that is, this is what really we are interested and we start with. Then from that we obtain a function which is this Laplace transform of it. It is denoted by the corresponding capital symbol, so one will write capital U, and the value of the function u at time t, for example at 0 or 5 or 10 raised to 5, the general value at time t will be indicated as ut. So in particular u0 will denote the value of the function at t equal to 0. Correspondingly for the Laplace transform u, the value at a general complex number will be denoted as capital U of s. For example, we can talk about capital U at 2 plus j3. This one, the u or the original function as it is called, is usually real valued. Ut is real. It is a function of a real variable because t is a real number. Time for us is a real number, and I told you that as control people we are interested usually in what happens after or starting with some initial moment of time, which for most purposes one denotes by 0. So the t here is usually restricted to p greater than equal to 0, and then we obtain the function capital U, which is the Laplace transform of the function small u, but the number s here, or s, can be replaced or will denote a complex number in general, and u of s will also be a complex. So u will be a complex valued function of a complex variable s. The symbols t for time and the symbol s for the Laplace transform integral are fairly standard. In some books, some of the older books, you might find the letter p in place of s. So don't be surprised. In fact, some of the people who worked with this earlier, one of them was, you could call him more or less an electrical engineer. He himself preferred to be thought of as an engineer rather than a mathematician. He made very important contributions not only to what we are talking about, not control, but generally the study of system behavior, inputs, outputs, and so on. But he also made contributions to electromagnetic theory, and this person was Heaviside. Heaviside used the letter P rather than the letter S, but subsequently the letter S has become very common, just as in electrical engineering practice usually F, in communication theory at least, will stand for frequency rather than for be the symbol for a function, whereas in mathematics one would talk about f of t or ft. In communication theory, the letter f is preferably used for frequency in hertz, and as you know, the letter omega in electrical engineering is preferably used for what is called angular frequency, or omega equal to 2 pi f in radians per second. However, for our control theory purposes, the letter omega is also very commonly used for angular velocity. In fact, in control theory, one usually does not use omega or f in any significant way, because in control theory we are not interested only in the sinusoidal function. In fact, we are interested in many other functions other than the sinusoidal function, and therefore the symbol omega in control applications will usually denote speed, because speed control is one major application of control theory. So don't be surprised if you find other notations, but this convention that a capital letter will denote the Laplace transform of a function which is denoted by a small letter is also more or less very commonly used. So this is the Laplace transform or the Laplace transformation. We say that the function small u is transformed into the function capital U, and therefore we talk about the Laplace transformation. The transformation applied to u results in a different or a new function capital U. Now, what is the use of the Laplace transformation? As I told you, the Laplace transformation began to be used for the study of differential equations essentially not more than 100 years ago, or maybe a little over 100 years ago. And I mentioned Heaviside just now. Heaviside was one of those who started using the transform idea for studying differential equations. Laplace gave his integral around 1800, almost 200 years ago, but his purpose was a little different. He was more interested in problems in mechanics. So how shall we use the Laplace transformation then to solve a differential equation, and why is it useful? Well, the Laplace transformation is a useful technique for solving differential equations, but not all kinds of differential equations. The Laplace transformation is a useful technique for solving differential equations only of a particular kind. And what is that kind? First of all, it should be an ordinary differential equation. In other words, there should be only one independent variable. Fortunately, in the control theory situation, usually there is only one independent variable, namely time. Although there are occasions where in place of time you may have a single space variable as the independent variable. Indeed, there are some applications in what are called flexible structures, where one may, instead of time, think of distance as an independent variable. So the differential equation should be an ordinary differential equation, not a partial differential equation. Only one independent variable, and for us usually most of the time it will denote time. Dependent variables, of course, there can be many. There can be the angular speed, there can be angular position, voltage, applied voltage, current, torque, whatever, any number of independent variable, dependent variables you can have, but they should all be functions of one independent variable t. So ordinary differential equations, not partial. So the derivatives that occur will be only ordinary derivatives, not partial derivatives. So things like du dx, partial derivative of u with respect to x, will not occur in our work. The derivative will be what then are called sometimes ordinary derivative, or it's a function of only one variable. So that's one. Secondly, the differential equation must be of the kind that I mentioned earlier, namely linear differential equation, but not only just linear, with constant coefficient. Linear differential equation with constant coefficient. The Laplace transformation is a useful technique, or the use of the Laplace transformation is a useful technique for solving ordinary linear differential equations with constant coefficient. Now once again, with the development of computers, with their becoming comparatively cheap, very fast, with very large memory capacity, the use of the Laplace transform is restricted more or less for, if at all you want to solve a problem, for solving lower order problems, maybe first order differential equation, or second order, maybe third or fourth. If you had a 100th order differential equation, you may not use the Laplace transformation method. But that's not the only use of the Laplace transformation. As I told you earlier, quoting Hamming, the purpose of computing is insight, not numbers. So similarly, by the use of the Laplace transformation, we can get some insight about the behavior of systems. We can find out, using the Laplace transformation, if not exactly how the system will behave, that is, the output signal at 10 seconds will be precisely this, and so on. That of course we can calculate, but something qualitative about the behavior of the system or of the variable. For example, we can say that the speed of the motor, as the motor starts and builds up to its final speed, will keep on increasing steadily, or the speed will overshoot the steady state value, that it will increase, but unfortunately it will cross the steady state value, so it will overshoot, then it will stop increasing, then start decreasing, but on the downward turn it will again cross the steady state value, and so there will be what is called an undershoot, and then again an overshoot, and so on. So whether the speed will behave like this, build up steadily to the final value, or will have decaying oscillations with overshoot and undershoot, qualitatively the use of the Laplace transformation plus something more will tell us. Actual computation of the peak value, etc., will require numerical work associated with the Laplace transform or the Laplace transformation, and as I told you, there are packages today which will solve differential equations and plot the results for you. So it is not necessary really to do it. If you wanted to calculate with some precision the response, to use the Laplace transformation, but no amount of computer program will give you this insight about what kinds of behavior to expect, and so on. So for us, the Laplace transformation is a tool mainly for getting insight into the behavior of system, rather than for doing lots of computations. Keep that in mind. So do not underrate it. At the same time, do not try to use it for everything. Okay, so how is the Laplace transformation to be used for solving or finding out what happens to a system described by, say, a first order differential equation or a second order differential equation, and so on? Now, the Laplace transformation, one can show, has some properties. It has quite a few properties in fact, and your textbook of control theory will probably give you a list of properties of the Laplace transformation. If it doesn't, certainly a mathematics textbook which talks about mathematics of engineering or engineering mathematics will have a chapter on the Laplace transformation and will list quite a few properties of the Laplace transformation. For the immediate purpose of trying to solve a linear differential equation with constant coefficient, we require only a few properties of the Laplace transformation. In fact, you require only 3 properties of the Laplace transformation, and I will show you that with the help of these 3 properties, not only can we make some progress towards the solution of the differential equation, but we can also almost calculate the Laplace transform of a few functions, not all, a few functions. We will see how. But first, the properties of the Laplace transformation that are going to be useful. Now, these properties have to be understood properly. First of all, recall once again that the Laplace transformation transforms one function, usually regarded as a function of time variable, into another function. And one more thing, I mentioned that in control we are interested in the values of time greater than or equal to 0, and therefore such functions are called one-sided functions. We are interested only in one half of the time axis, starting from 0 and going on towards the future. I have been showing it like this. This is 0. We are not interested in the other half, but it is possible. In fact, in communication theory, one likes to think of functions whose past behavior also may be useful or important. In that case, it is possible to talk about a different Laplace transformation, that is, it is like the Laplace transformation but not quite what we had, and then we have therefore a two-sided function and a two-sided Laplace transform. If you remember, the Fourier transform is a transform for which the function is supposed to be defined for all time t, whether t equal to 0 or t greater than 0, that is future time, or t less than 0, that is past time. The Laplace transformation that I am going to talk about and we are going to find useful is a one-sided Laplace transform. So, functions defined only for t greater than or equal to 0, the Laplace transformation, one says, changes or transforms or converts this function of time into a different kind of function, into a complex valued function of a complex variable, usually denoted by s. Now, this transformation, this action has some special properties. The first property is what is called additivity. We will say, or one says, that the Laplace transformation is additive, is an additive transformation. What does that mean? Suppose I have two functions of time, one denoted by u1, another denoted by u2. u1 denotes a function of time, u2 denotes another function of time. Let us say u1 is some signal, u2 is some other signal. Then I can certainly think of a function which is obtained by adding these two functions. In fact, we most often talk about such functions. The sum or the result of adding the two functions is of course denoted by u1 plus u2. If I want to show the time argument explicitly, then I will write u1 of t, that is the value of u1 at t, plus the value of u2 at t. This sum is the value of a new function which is denoted by u1 plus u2. Its value at t is u1 of t plus u2 at t. The symbol delta tells you that the function u1 plus u2 is being defined this way. And this is just notation, but one has been writing sums of functions of time. For example, if I write t minus e raised to minus t, or maybe you see a minus sign, so you may not see a sum right away. So, suppose I write t plus e raised to minus t. This is a sum of two functions. One function whose value at t is t itself, another function whose value at t is e raised to minus t. So this is a function which is the sum of two functions. So if we have two functions u1, u2, physically there could be two voltages, two currents, then we can think of their sum u1 plus u2. Now we could, as one puts it, apply the Laplace transformation to the function u1. If I apply the Laplace transformation to the function u1, the resulting function, as we have agreed, will be denoted by the corresponding capital letter. So we will read this as L applied to u1 results in capital U1, or the Laplace transform of the function small u1 is the function capital U1. Similarly, I apply Laplace transform to u2 to get the function capital U2. Then I can ask the question, what will be the result of applying the Laplace transformation to the function u1 plus u2? Just one thing to remember here, going back, the Laplace transform usually has a region of convergence, which means that LU1 is capital U1, but the function u1 is defined only for certain complex numbers s, namely the region of convergence of u1. Similarly, LU2 or capital U2 will be defined or will make sense only for certain complex numbers s. Now if I want to talk about L of u1 plus u2, then again I must talk about the region of convergence of u1 plus u2. So the result that I am going to write has to be understood correctly, that is, it's only for numbers, complex numbers s, which belong to the region of convergence of all the functions that are involved. For such complex numbers s, what is L of u1 plus u2? L of u1 plus u2 is a function which happens to be the sum of u1 and u2. So one reads it as the Laplace transform of the sum of two functions is the sum of their Laplace transforms. Or if I write it more explicitly, L of u1 plus u2 equals L of u1 plus L of u2. On the one hand, I add two functions of time, then take their Laplace transform. On the other hand, I apply the Laplace transform first and then add them. These are functions of time, these are functions of s, but I am adding here because I can add two real numbers. I am adding here because I can add two complex numbers. L of u1 plus u2 is LU1 plus LU2. This is the property of additivity, and one can immediately see a use for this, because if I have two functions whose Laplace transforms I know, then the Laplace transform of their sum also I will be able to calculate almost immediately. For example, if you look up your textbook of mathematics or control theory, you will find actually a table of Laplace transforms. That is, you will find a list of functions, they may be denoted by f or u, it does not matter, and their corresponding transforms, capital Fs or capital U of s. The function whose value at any time t is t, remember only for t greater than or equal to 0, its Laplace transform is the function whose value for certain complex numbers s is given by 1 by s squared. If the function is simply the constant function 1, it is sometimes called the step function, the unit step function, the function whose value is just 1 for all time t greater than or equal to 0, its Laplace transform is given by a function whose value for some complex numbers in the region of convergence is 1 by s. For sine of t, I have already told you that the Laplace transform is 1 over s squared plus 1. For e raised to minus t, the Laplace transform is simply 1 divided by s plus 1. For a general exponential e raised to at, the Laplace transform is 1 divided by, and this is where one has to take care, if there is at here, there is a minus sign here, the Laplace transform is 1 divided by s minus a, or if I write e raised to minus at, then the Laplace transform is 1 divided by s plus a. I am almost writing a part of a table of Laplace transforms. So let us use this for calculating the Laplace transform of the function t plus e raised to minus t. The Laplace transform of t is given by 1 divided by s squared for certain complex numbers s. The Laplace transform of e to the minus t is given by 1 divided by s plus 1 again for certain complex numbers s, and for those complex numbers for which this holds and this holds, for those complex numbers the Laplace transform of the sum is given by the expression 1 over s squared plus 1 over s plus 1. So if you know the Laplace transform of two functions, you can immediately state what the Laplace transform of their sum is going to be. This is the property of additivity. The next property, which is useful in solving LDEWCC, is a property which is known as homogeneity. Or it has something to do with scaling of a function. I have a function u, let us say it is some speed or whatever, and I multiply it or scale it by a scale factor. Usually for such multipliers or scale factors, as you know, one uses letters from the Greek alphabet like alpha, beta, lambda and so on, or letters like k, etc. as coefficients. So if I have a number lambda, real number lambda, I can scale my u by this scale factor lambda. For example, lambda may be 10, so I have the function which is 10 times the original function u, or lambda may be 10 raised to minus 3, so I have a function which is an attenuated version of the original function u. So this is referred to as scaling. U is scaled by lambda, by the factor lambda, to get a new function lambda u. What will be the Laplace transform of lambda u? Well, using the integral, you should be able to show that the Laplace transform of the integral will be simply a Laplace transform of the multiple, the scaled factor lambda multiplying u will be simply a multiple of the Laplace transform of the original function. So it will be lambda times us, and it turns out here that the s is the same for both u as well as its scaled version. That is, the region of convergence for u and lambda u, the two functions, the original function and its scaled version, the region of convergence is the same. So for whatever s, capital U of s is defined, for the same s, the Laplace transform of lambda u also is defined, and it is given simply by the same multiple. So what is the use of this? Well, I know that the Laplace transform of e raised to minus t is 1 divided by s plus 1, and therefore if I have the function alpha into e raised to minus t, I am changing from lambda to alpha because one should get used to these various symbols, then what will be the Laplace transform of alpha times e to the minus t? It will be simply alpha times 1 divided by s plus 1, or as you know, one prefers to write alpha in the numerator like this, so it is alpha divided by s plus 1. This is the property of homogeneity. So the Laplace transform is a homogeneous transformation, or it is a transformation which has the property of homogeneity. The Laplace transformation is also an additive transformation. It is a transformation which has the property of additivity. Now because it has both these properties, one can go further. For example, I have the function which is given by 3t minus 4 e raised to minus t. What is the Laplace transformation, or what is the Laplace transform of this function, or the result of applying the Laplace transformation to this function? Now one can immediately see that this is a sum, and the minus sign need not worry us, because I can write this or think of it also as 3t plus minus 4 times e to the minus t. Either I multiply e to the minus t by 4 and subtract it, or I multiply it by minus 4 and add it. The result is the same. So what do I have? I have a function which is a sum of two functions, so my additivity can be used, but each one of them is a multiple of another function. 3t is a multiple of t, multiplying factor 3, minus 4 e to the minus t is a multiple of e to the minus t, the multiplying factor is minus 4. So what is going to be the Laplace transform of 3t minus 4 times e raised to minus t? And I am showing it this way, that is, this function is transformed into what function of s? For t it was 1 by s squared, but now I have 3 times t, so I will have 3 divided by s squared. For e to the minus t it was 1 by s plus 1, but now I have minus 4 times that, and therefore I will write it as minus here and 4 here, or I can write alternately plus and with minus 4 in the numerator of the fraction. So the Laplace transform of this function 3t minus 4e to the minus t is the function 3 divided by s squared minus 4 divided by s plus 1. And of course, what applies to a sum of two terms here will apply to a sum of 3, 5, 50, 100, whatever number of terms, with different multipliers here 3, 4 or minus 4 and so on. I don't have to state separately a result that the Laplace transform of u1 minus u2 equals the Laplace of u1 minus the Laplace transform of u2, because u1 plus u2 can also be regarded as u1 plus minus 1 times u2. So we have two properties of the Laplace transformation so far, and we can see how they are going to be useful. If we know the Laplace transform of some functions, we easily get the Laplace transform of their multiples. We get also the Laplace transform of their sums or sums of different multiples of them. So starting with say only t and e raised to minus t, I can build a whole class of functions. For example, alpha t plus beta into e raised to minus t. This is not just one function. For each choice of alpha and beta, it gives me a function. So it gives me infinitely many functions parameterized by alpha and beta. I can find out the Laplace transform of each and every one of them, because I know the Laplace transform of t, the Laplace transform of e to the minus t, and because I know and remember these two properties of the Laplace transformation. If you did not remember those properties, then you would struggle with this, multiply by e raised to minus t, integrate from 0 to t, find out the integral, take the limit of it as t tends to infinity and all that stuff. But if you remember the two properties of the Laplace transformation, and if you remember the Laplace transform of the two functions that are occurring here, then the Laplace transform of all such sums, each one of them can be found out quickly. Now the third property of the Laplace transformation, which is the property that makes it useful for the solution of differential equations. And the third property therefore involves a derivative, and therefore I am going to call it the derivative property of the Laplace transformation. It is a property that involves derivative, and it is a property that makes it useful for the solution of differential equations. The differential equations have derivatives. The Laplace transformation has this nice property, as we will see, and therefore we can use it for the solution of differential equations. What is the derivative property? We have to be a little careful with this, and as I told you, there is always the region of convergence, etc. So I am not going to state the result in its fully rigorous form, that is in its fully correct form, but it is good enough for our purpose. So let us say I have the input signal u, or I have the signal u, or the function u, and this function u is differentiable, that is, it has a derivative. Unfortunately, not all functions are differentiable, although most of the functions that we come across as engineers are differentiable. But there are functions which are not differentiable, and there are functions which can even occur in an engineering application which are not differentiable, or at least not differentiable at some points, as we say. Incidentally, there are some functions, in fact there are many functions for which the Laplace transformation does not apply at all, because the Laplace integral does not converge at all. No complex number s, that integral ut e raised to minus st dt from 0 to t, limit of that as t tending to infinity, may not exist for any complex number s whatsoever. There are such bad functions, but there are mostly for us good functions which occur in our practice, which are, one says, Laplace transformable, that is, for which the Laplace transformation can be applied in the sense the Laplace integral converges for at least a large set of values of s. So here is the function u. I am going to assume that it is Laplace transformable, that is, for some s, capital U of s is well defined. Then I am assuming that the function is differentiable. Then I am going to assume that the derivative, and by now you are familiar with this notation, so I am not going to write du by dt, I am just going to write capital Du, meaning the derivative of u, or in fact the derivative operation applied to the function u produces another function. The derivative operation applied to the displacement function produces the velocity function. So u the derivative of u. I am going to assume that the derivative of u is also Laplace transformable. So, I can talk about L of that. So, that is a function of s. On the other hand, I can talk about L of u, that is another function of s. What is the relationship between these two functions? The Laplace transform of the derivative and the Laplace transform of the original function, or to put it the other way, the Laplace transform of a function and the Laplace transform of its derivative. There is a property, and that is what is called, I am going to call the derivative property of the Laplace transformation. However, that derivative property requires care to apply and is a little more difficult to remember than the additivity and homogeneity. I am just going to write it at the moment, and we will look at it in more detail by taking specific examples. The derivative property can be stated as follows: Lu and Ldu. What is the relationship between the two? Well, the relationship is given by Ldu, the Laplace transform of the derivative function, its value at a complex number s, such that this Laplace transform exists for that complex number s, is given by s times the Laplace transform of u, its value at s, minus a number which is written as u, and I am going to write here 0 plus. There are two terms here on the right hand side. There is the Laplace transform of the original function, but that gets multiplied by the complex number s. But that is not all. There is something that gets subtracted, namely minus u0 plus. What is this u0 plus? This u0 plus is what is called the limit of the function u at time t equal to 0, but this 0 plus tells you that it is the limit from the right, and that is because of a technical mathematical problem that I have to talk about the limit from the right rather than u0. For many functions, of course, in place of u0 plus, I can simply write u0 and the result will be correct, but the precise result, the correct result of the Laplace transformation theory would have it like this: the Laplace transform of the derivative, its value at s, is s times the Laplace transform of the original function, the value of that at s, minus u0 plus, the limit of the original function at t equal to 0, but the limit from the right. Now, you can see how this might be useful, because on the left hand side I have the derivative of u, but on the right hand side I do not have the derivative. So, sort of I have got rid of the derivative by taking the Laplace transformation, or by applying the Laplace transformation, and we will see that this is what makes it useful for the solution of what kind of equations? Ordinary linear differential equations with constant coefficients. We will take some examples to illustrate this. First, the derivative property, and then its use for solution of a differential equation of that kind.